Hello everybody, you are welcome to this 12th lecture session of database management systems. In this session, we discuss about hashing techniques that are employed for fast retrieval of the records from the database. We discuss introduction to hashing, what is internal hashing and what is the phenomena of collision, external hashing, static hashing, then we discuss about the dynamic hashing techniques. Hashing technique is an alternative to indexing, and of course in next few classes, in the next class we will be discussing about the technique called as indexing, and wherein indexing as well as hashing, these are the techniques for fast retrieval of data records based on the search key. The search field in hashing is called as a hash field, that is based on what field value we are searching for records is known as a hash field. In most cases, the hash field is also a key field of the file. That means, file means what? Normally a data pertaining to a relation in database is stored in a file. So, that is why the key field of that file normally becomes the hash field, in which case it is called as a hash key. If the key is the hash field, then it is called as a hash key. If it is not a key, it is just called as a hash field. The basic idea of hashing is that hash function h, there will be a hash function called h which does some computation, and when it is supplied with the value field value k of a record, it does some computations and then produces the b, which is nothing but the address of the block where a record with the specified key value k is stored. So, this is how the hashing works. Hash function h is a hash function which does some computation. If you look at this, h is a function which is called as a hash function and which has some computations involved, and when the key value is supplied, whose value, where this key is a hash key or hash field based on which we are making a search in the database for a given record, it does whatever is the computation specified for this hash function, and it produces a value which is called as the disk block address. Once the disk block address where a record with a specified key value is stored is known, then actual search for the actual record, because a block may contain more than one record, but still for the purpose of processing the record, we need to bring the entire block from disk to RAM, then only we can process the record or value in a record. So, that is why once the disk block address is known, then automatically the block which contains that record on the disk is transferred to the RAM, and then actual search for the record is actually takes place in the RAM main memory. Of course, the search for a record in a block when it is carried out in main memory, it is going to be very fast. So, that is why the time consumed for that is very less. The main problem is how to identify a block where the record is stored. That is important. To alleviate that problem, to make it possible, the hash function is there. When it is supplied with the key value, it will produce b, which is nothing but the block address. For most records, we require only one block access. That is the advantage or beauty of this hashing technique. Of course, in indexing technique, what we are going to discuss in next classes, it is the how many block accesses are required to access a record. It depends on the indexing technique you are using, the indexing structure that is being used, so on and so forth. But whereas in the case of hashing technique, most of the cases only one block access is required. First, let us talk about internal hashing. We have two hashing techniques. First one is internal hashing, second one is external hashing. Internal hashing technique is employed for files or blocks which are available. When you need to do some hashing on the files in RAM, then it is internal hashing is used, and for the files which are on the disk, if you want to provide hashing, if you want to do hashing, then it is called as external hashing. Internal hashing is used for internal files, that is the files on the RAM. A hash table is implemented through use of an array of records. If you see here, this can be seen as an array of records. The most common hash function that is used is equals to k mod m. K is the key value, m is some value which is nothing but how many locations or array locations are there in the array, that is m. and then modulo division function is used. Given this example, how many locations are there? It is starting from 0 and it is going up to m minus 1. That means we have m number of locations in array. Now whenever I insert a record with some key value k, and it should go into one of these 0 to m locations. This gives, so when you apply this mod function or the hash function, which is k mod m, and this gives the index of the location in the array. For example, let us assume that there are 10 locations. The m is equals to 10. This is m. And suppose if I am inserting a record with key value 24, what is going to happen? K mod m, that is 24 mod 10, which is modulo division always gives the remainder. So that's why it is going to be 4. Hence the record with key value 24 is the result of the applying hash function is 4. Hence it should go to the location, that is array location 4. The record with key value 24 is stored at array location 4. And if at all there is a record with the value 20, key value 20, where it should go? 20 mod 10, which is equal to 0, it should get into the 0th location, so on and so forth. Hence the record with key value 24 will be stored in 5th location. Location 4 means, index 4 means, since it is starting at 0, it is a 5th location of the array. Sometimes what happens, let us assume that I have stored a record with key value 24, and further now I want to store a record with key value 64. Now what happens? 64 mod 10, again it gives you 4. Again this is also hashed on to the same location. When 2 or more records are hashed on to the same location, this phenomena is called as collision, and that need to be resolved. Then we need to find some solution or find other location, using which we will find other location for the new record, and this process of finding a new record, new location for the new record when there is a collision is called as collision resolution. It is called as collision resolution. Methods for collision resolution are as follows. The first method I can adopt is open addressing. When collision occurs, try with alternate cells until an empty cell is found. Then you can insert that record. It is not formed, it is in fact it is found. So when you find an empty cell, then you insert that new record which caused the collision. That is the first approach. Second approach and most popular approach is chaining. For this, various overflow locations are kept by extending the array by number of overflow positions. A pointer field is added to each record location. Collision is resolved by allocating an unused overflow position in this overflow area. Let us have a look at this example. Okay, now we discuss about an example on collision resolution using chaining. In this case, let us assume that the original address space, the number of locations for storing the records is called as address space. Otherwise, the possible values for the result of applying hash function on any key value is called as the address space. In this case, let us assume that m is equals to 5. That means I have 5 locations starting from 0 through 4. So this is the original address space, actual address space. Now to resolve the collision, whenever a collision occurs, I apply chaining to resolve that. I have some overflow space available. That means some locations are specified which are called as overflow locations, and then each record is also coming with a overflow pointer, and of course a data item is stored. Along with that, a overflow pointer is also stored, which whenever there is a collision, which points to the next record which has the same hash value or hash function result, and then it indicates the location of that record. Okay, let us have a look at the example. The hash function used is k mod 5. First I am inserting 12 value, key value 12. 12 mod 5 is equals to 2, so it will get into this location. Second, that is the third location with index 2. Inserting 20, the result is equals to 0, that will get into this location. Then insert 17 mod 5, again it is 2, it is pointing to the location with index value 2, hence there is a collision, because that location is already occupied by some other record with value 12 and which was also hashed onto the same location, then there is a collision. Now what I will do is, I will go to the overflow space, I will find some free location for the new record, that is with value 17, I will insert it there, and in the original address space for the record which is having 12 and there is another record with 17 which is also hashed onto the same location, then I will make a pointer, overflow pointer to the location where the another record with the same hash value is stored, hash result is stored. So that is why now if I am making a search, 17 is stored at the location index 5. Now then when I am inserting 36, 36 mod 5 is equals to 1, it will get into this location, and when I am inserting a record with key value 2, 2 mod 5 is equals to 2, again it will hash on to the same location, but it is already full. I will take the pointer 5, I will go to that location, it is also full, and now I will find some other location which is free and then insert the new record there, and then I will indicate the pointer to that location using a overflow pointer in the previous record in the chain. That is, there is two indirections are there. From record 12 I am able to reach the location where the record 17 is inserted available, and from there using one pointer I am able to reach the location where a record with key value 2 is available. So this is how we can resolve this collision. Suppose in this case, if I am making a search for a record with key value 2, suppose I want to, now this is insertion, whatever I have discussed, it is putting the data into the database. Now further at later point of time, for the purpose of manipulation or processing, you may need to extract the data. Yes, let us assume that I want to figure out a record with key value 2. Then I will same process, I will apply the hash function 2 mod 5, the result is going to be 2, hence I need to, it is possible that I will find that record with key value 2 at index location 2 in the array. When I go there, the whatever record is there, it is not 2, it is 12. That means it is not the required record, but it is possible that there may be a chaining, okay, there may be a overflow location which contains a record with the same result, hash result. So that is why I will take the pointer and then go to the location in the overflow bucket with there I find a record with value 17. This is also not the required record. Hence again, since there is one more indirection, I pick up that pointer and go to the location which is pointed by that pointer. Now here in this location I find a record with key value 2. That is, in this case, since there was a collision, I am using 2 levels of indirection to get the actual record with the given key value. Suppose if I am making a search for record with value 8, 8 mod 5 is equals to 3, I go to location 3, but it is empty, that means no record is available. That means it says that a record with key value 8 is not at all existent in the database, and if at all I am looking for a record with key value 36, 36 mod 5 it is 1, directly I will go to 1, there is only one record available, and that is the record with the required key value, and if there is no pointer it will be grounded, that means it will be a null value there. This is how the collision is resolved by using the method chaining. The one more approach for collision resolution is multiple hashing. That means I can apply multiple hashing functions. First I will apply first hash function which is h1, and for example let us consider that it is k mod 5, that is the first hash function. If there is a collision, I will apply the second hash function h2, and which could be k mod 10, and again if there is a collision I can resort to open addressing or I can adopt chaining, and this is called, that is, instead of using one hash function I will be using multiple hash functions in conjunction with other techniques. This is the third approach to resolve collision. This is called as internal hashing. Now let us have a look at what is external hashing technique. We understood that external hashing technique is used for files which are stored on the disk. Hashing used for disk files is called as external hashing. The disk block contains records. Actually, we know that a file contains disk blocks, and disk blocks actually contain records for a given relation or database. A single disk block or cluster of contiguous blocks is known as a bucket. This is a concept that is used in external hashing. That is, a bucket may be a single block or a cluster of contiguous blocks. The hashing function maps a key value into a relative bucket number. It is not directly going to give you the physical block address. Rather, in external hashing, on applying a hash function, the result is nothing but a relative bucket number. A table is maintained, a table structure is maintained, and where it will map the bucket number, which is result of applying the hash function to the appropriate physical disk block address. So, this is how the external hashing is done. A table maintained in the file header converts the bucket number into corresponding disk block address as shown in the figure. And suppose, let us assume that there is a hash function h, and then when applying a key value, if it is giving the result as 2, then it is not the block address, rather it is the relative bucket number. I go to this directory structure or the table and look for the entry with value 2. So, this is the entry, and here I find a pointer or block address, nothing but a pointer, which will take me to the actual physical block where a record with key value k is stored. So, that is why in external hashing we have buckets. A bucket can be a single block, most of the time it is a single block on the disk, or it could be cluster of contiguous blocks. Okay. Then whenever we apply a hash function on the key value k, it gives some value that is nothing but the relative bucket number, not the block address, and then make a search in the directory, that is in the table, which maps this relative bucket number to the actual block address on the disk, and then go to the block and then get the required record. This is how the external hashing works. This diagram, it says, it describes how it works. Matching bucket number to disk block address is provided by, facilitated by this table. These are the bucket numbers, and immediately you will find a block address on the disk. You see here, 0th block is this physical block. First block, that is the next block, next bucket number is mapped on to some other block which is located at some other place. There need not be at contiguous locations. Okay, this is how the mapping happens. It is also possible that the above scheme is called as static hashing, because the number of buckets allocated is fixed. That is, if I am using a hash function hk, which is nothing but k mod 10, what happens then? What is the possible values for this? You give any key value, since m is equals to 10, there could be only 10 possible values starting from 0 to 9. So, this is called as the address space, and that means there could be only 10 logical buckets possible according to this hashing, and it cannot change over the time. That is why it is called as static hashing, because the number of buckets allocated is fixed. This is a big constraint for files that are dynamic. What happens with the dynamic files? The file initially may contain 2 buckets, and as and when you keep on inserting or pumping in more number of records, the number of buckets allocated for that file may become more and more. That means a dynamic file, depending on the requirement of the application and the database, then the number of blocks may increase or go down. That is why it is dynamic. It may shrink or increase, expand. So, that is why this is hence the address space that has been allocated, the number of buckets that have been allocated using a hash function, they are always fixed. This is called as hashing, static hashing technique, and this is a big constraint for files that are dynamic in nature. When a bucket is filled, so what they do in static hashing, if a bucket is full, that means if more number of records are hashing onto the same location, the sooner the bucket is filled with records, then when a bucket is full to its capacity, and if the new record is hashed onto the same bucket, then the chaining is adopted where a pointer is maintained in each bucket to a linked list for overflow records for the bucket. So, chaining is again possible here because the available address space is fixed. The pointer or record pointers, which include both the address and relative record position within that block. So, that is why at every block, at every end of end of each bucket, we include a record pointer which points to the overflow bucket, which can contain the collided or overflowing records for that particular bucket. This is how we resolve a collision in this static external hashing. Let us have a look at this. You see here let us assume that the function is, that is HK, hashing function is k mod 10. When a record with 340 is inserted, that is how many buckets are possible? Maximum 10 buckets are possible, starting with 0 to 9. So when a record with 340 is inserted, that is 0, 1, 2, 3, 4 up to 9, the record with 340 mod 10, that gives you the value, that is result of applying hash function is 0. That means it should go to bucket number 0. Then we go to the value, the result is 0. Hence we go to the table and make a search for an entry with value 0. Then this will point me to this bucket. Hence a record with 340 is inserted in bucket 0. This is the physical block, and this is the table which is used for lookup to find out the address, physical block address for the bucket number, which is the result of applying the hash function. 340, when I apply k mod 10, the result is equals to 0. Then I go to the table and find out the address of the bucket, actual bucket, and then go there and then put the record. When I insert 321, let us assume that next I am inserting 321. 321 mod 10, which is equal to 1, I go to the table and this is the entry for 1. This will make a point to this bucket where the record with 321 can be stored. Next I am storing 460. 460 mod 10, again 0, I go to the same bucket and put it there. Let us assume that each bucket will take only 3 records, and then when I insert 761 mod 10, it is 1, it will be stored here. 91 is also 1, so it will be stored here. And then when I try to insert a record with key value 981, what is the result of applying hash function? 981 divided by 10, that gives me 1. That means again I will be pointed to the same bucket, that is bucket number 1. But if you carefully observe, all the locations are filled with the existing records, that is 321, 761, 91, all have been hashed onto the same bucket. Hence it is already full. Now I need to insert a record with key value 981. I don't find enough space there. Then I can create a overflow bucket here. This is the overflow bucket, and then at the end of the bucket where the collision has occurred, I have a record pointer which is pointing to the location in the overflow bucket where the collided record with key value 981 can be stored. So this is where I can store it. And if you take this bucket 2, 22 has been hashed onto the same location bucket, 72 is also hashed onto the same bucket, similarly 522 as well. When I now try to insert a record with 182, it is also 182 mod 10 is 10, 0, sorry, it is 2. Again I go to the table and pick up the entry with value 2. This is pointing me to this bucket, and but it is already full. Only it can accommodate only 3 records. Already 3 records are existent in the bucket. Now what should I do? Again take a overflow pointer, which is a record pointer pointing to the location in some overflow bucket. Okay. Now this pointer will take you to the location where I can insert a overflowing record, that is with key value 182 in overflow bucket. And one important point to be noted is a overflow bucket can accommodate records which are overflowing from multiple buckets, that is different buckets, that is possible. You see here, this is the record which is the result of overflow in bucket 1, and 182 is the record which is overflowing from bucket number 2. Hence a same bucket, overflow bucket, can accommodate overflowing records from different original buckets. Then still once this overflow bucket is also full, let us assume that I am inserting a record with key value 252. Again it will hash on to 2, and in the table the pointer will take me to this bucket, but it is full. I will take this pointer, overflow pointer, go to this location, and it is not there is no space. Again I find some space in some other overflow bucket and I can put this here and then make a record pointer and then make it to point to that location which is another overflow bucket. Since it is static external hashing, and when the size of the file grows, that is when you have more number of records inserted, it is more likely that it may lead to more number of collisions. When there are more number of collisions, more number of overflow buckets are required, and that results in more number of more chaining, and again the purpose is defeated. That is one big constraint of this static external hashing. And again, if you go back to this static external hashing, so this is the table structure. The result of hash function will have an entry in the table. Go to that table and find out that entry, and immediately next to that you can find the block address where the record with the key value is stored. You go to that block and then transfer that block into the RAM and then use it for processing. This is static external hashing. That is, the address space is fixed, hence I cannot allocate more number of original buckets for the file, and whenever the size of the file grows, it results in more amount of chaining, which actually defeat the purpose. And to resolve that, to overcome that, the dynamic hashing has been introduced. This scheme allows us to expand or shrink the hash address space dynamically. That is, the hash address space can be expanded or it can be reduced or it can be made to shrink depending on the requirement. Each result of applying the hash function is a non-negative integer. The concept behind dynamic hashing is, when you apply a hash function hk, that gives you some value, and this value, result of hash function is a non-negative integer, and now we can always convert this non-negative integer into its binary representation, which is in terms of zeros and ones. For instance, if I have the hash function k mod 10, let us assume that it is k mod 10, and then if the record with key value 12 comes, what is the result of this 12 mod 10, which is nothing but 2? What is the binary equivalent of 2? It can be represented like this. This is the binary representation of 2, and if it is 8, it is going to be 100 something like this. So the result of applying the hash function in dynamic hashing or any hashing is a non-negative integer, and of course that can be converted to binary equivalent figure. So that's why each result of applying the hash function is a non-negative integer and hence can be represented with a binary pattern, that is in terms of zeros and ones. This we call it as hash value. The binary representation of the result of applying hash function is called as the hash value. In this case, this is known as the hash value. Hash value is always in binary representation. Records are distributed among the buckets based on the values of the leading bits, or using this based on the value of this hash value. And here in dynamic hashing we have two approaches. First that is, in dynamic hashing we have extendable hashing, and then next one is linear hashing. First we will discuss about extendable hashing. The first technique is called as extendable hashing. This scheme stores a directory structure in addition to the file. This access structure, this directory structure is also called as an access structure, and which provides access to actual buckets. This access structure is based on the result of applying the hash function to the search field. The major advantage of extendable hashing is that performance does not degrade because of chaining. Of course, you have some amount of chaining, but it is very minimal, and dynamically the address space can be changed. Hence, the performance will not degrade because of chaining. As the file grows, as we have seen in the static hashing, that degradation of performance is there due to increased amount of chaining, but that amount of chaining is very minimal, and it is completely controlled in this extendable hashing. Hence, the performance is going to be far better than static hashing, and when we are using dynamic files, this is the better way to use hashing technique. In extendable hashing, no additional space is wasted towards the allocations for future growth. If I am using static hashing and if I don't know how many records are going to be stored, if I allocate more number of buckets, and ultimately if there are no sufficient number of records, I will be underutilizing the space. And if I am allocating less number of buckets, as and when the size of the file grows, then I will end up with more number of chains or indirections. Hence, it is a problem in static hashing, and wherein it is not there in the case of extendable hashing. In extendable hashing, no additional space is wasted towards the allocation for future growth, but additional buckets can be allocated dynamically as and when it is needed. The only overhead in this scheme is that the directory structure need to be searched before the actual bucket is accessed for the required record, and this is the extendable hashing technique. We will have a look at the diagram which gives us the clear picture about this. This is called as the directory structure, and these are the actual data file buckets or data blocks. Suppose, let us assume that there is a function, hash function kmod 10. If I insert a record with the 24, what is the result of this? 4. What is the binary equivalent of this? 0 1 0 0. So this is called as hash value. I go to the, and I can use, that is, a binary representation of a given integer can be represented in 2 bits, 4 bits, 8 bits, 16 bits, so on and so forth. And once it is converted to binary representation using a certain number of bits, then initially I can use the most, that is the least significant bits or most significant bits to make a search in the directory. Here let us assume that I am going to use, as it is given in this, I will be using leading bits here. That means the result of applying hash function on 24, key value 24 is equals to 4, this is the binary representation. Of course, in this case let us assume that I am going to use 4 bits for binary representation of a non-negative integer. And initially the directory structure, the global depth, there is a notion called as global depth, which indicates that how many leading bits of the binary representation of the hash value are used to make a search. In this case, the global depth is equals to 3. That means I will be using, though there are 4 bits in the result or hash value, and I will be considering only 3 leading bits. When I have 3 leading bits considered, how many entries are possible in the directory? 2 to the power of 3, that is 8 number of entries are possible in the directory structure. That is what is there. So now the global, this for this mechanism, for this scheme, extendable hashing scheme, the global depth is 3. That means from the hash value, I will be always considering 3 leading bits. And when I have 3 leading bits that need to be considered for making a search in the directory structure or the access structure, then how many entries will be there? 2 to the power of 3, 8 entries will be there, and that is evident here. Okay. Now 0 1 0 0, 0 1 0 0, global depth is equals to 3. I take 1 0 0 as the search value. 1 0 0, this is the entry. I go to this location, I have a pointer which will take me to a bucket. For the buckets also, I will have local depth which is applied to this actual buckets. The local depth indicates how many leading bits of the hash value need to be used for identifying or deciding upon the bucket where the record with that key value can be stored. Hence, we have a directory structure, we have a notion called local depth, global depth, which is used for directory structure, and then we have a concept called the local depth, which is used for the actual buckets where we store the data. And we make the search for a required bucket using this directory structure. When we have a look at some example, then probably things will be more clearer than this. Okay, let us have a look at an example. Here the hash function used is kmod 10, that is the hash function. In this we have only one hash function, and the global depth initially is equals to 2. That means from the hash value we will be considering only 2 leading bits to make an entries or to construct the directory structure. This is the directory structure, and the keys or the records that need to be inserted into the file are first record with key value 32, second record with key value 28, then 43, 15, 66, 27, 86, so on and so forth. Okay, now when I apply the hash function on first key value 32, it results in 2. What is the binary representation? Here for binary representation, let us assume that I consider 4 bits. Okay, 2 is 0010, this is called as the hash value. 28 for key value 28, the result is 8 and it is 1000. For 43 it is 3, it is 0011, like that. For every key value I know what is the result of hash function and what is the binary representation of that hash result. Okay, now these are called as the hash values. Initially we can start with, depending on the requirement, we can start with any local depth or any global depth. In this case, let us assume that each disk block can accommodate only 2 records, and I start with the global depth is equals to 2 and then local depth is equals to 1. That means to deciding or making a search for an entry in the directory structure, I consider 2 leading bits of the hash value, and to decide upon the bucket where the record should be stored, I consider 1 bit of the hash value. Okay, now since the global depth is equals to 2, initially in the directory structure how many entries are required? 2 to the power of 2, I need 4 entries. This is my initial directory structure. I have 4 entries, 00, 01, 10 and then 11. Now when I insert a record with 32 mod 10, which gives me 2, and whose hash value is equals to 0010, and since the global depth is equals to 2, I take only last 2 digits and then make a search in the file 10, and this, since the local depth is equals to 1, how many buckets are possible? Only 2 buckets are possible. That means I have bucket 1 which will have records which are ending with 1 bit, that is leading bit 0, and this is the bucket which is going to accommodate all the records which are ending with hash value 1. Okay, initially 32 is hashed on to this 10, I will go here and then insert the record with 32. Then I insert 28 is equals to 1000, and again it is 00. Because the global depth is equals to 00, I will go to this entry and then go to this, because only one last bit for 00 as well as 10. Since when I consider global depth, these are distinct, because the global depth is equals to 2. When I consider the local depth which is equals to 1, these two are same, because I consider only last digit or most leading bit. So that's why both 28 and 32 are hashed on to the same location. Then I take up 43 is 0011, and 2 bits I will take, 11 will take me to this, and then I will put 43 here. Then it is 15 will be 01, and then I will go here, this will point me to this. Because the local depth is equals to 1, both 01 and then 11 will be pointing to the same location, and 00 and 10 will be pointing to the same bucket, since the global depth is equals to 2 and then local depth is equals to 1. Okay, up to this there is no problem. Now when I try to insert a record with the key value 66 mod 10 is equals to 6, and the binary representation is this, and then if I take last 2 bits, it is 10. If I take 10, that will take me to this location, but it is already full. So what can I do? Because the bucket can accommodate only 2 records. Now I cannot put a record with 66 there. Then I need to expand. That means I need to actually allocate one more new bucket. Yes, I am allocating one more new bucket. That means for this bucket, initially which had local depth is equals to 1, now I am making local depth of that to 2. That means that bucket is now initially 0, 0 and 10 both were pointing to only one bucket with local depth 1. Now I split it into 2 buckets. That means I allocate one more bucket. Now the 00, when the local depth becomes 2, 00 will point to a separate bucket and 1 0 will point to a separate bucket. That's what I have done. After splitting or expanding, now I will consider to distribute. Now initially when 66 was inserted, everything was hashed on to 32, 28 and 66. All these were hashed on to the same bucket. Now since there is a split bucket available for that, what I can do is, now I can redistribute these records based on the local depth 2. All the records ending up with 0 0 will get into this. All the records which are ending up with 1 0 will get into this. That's why 28 has gone into this and then 32 has gone into this. And if you carefully observe, still the local depth of the first bucket was increased to 2. Still the local depth of the second bucket is still 1. That means 0 1 and 1 1 are still pointing to the same bucket. And when I insert a value with 22, 22 is nothing but 27 is nothing but 1 1. I will go to 1 1, there is a space and then I will store it here. And now when I try to insert 57, there could be a collision. That is, when collision occurs, when there is a when the local depth of a bucket where the collision has occurred is less than the global depth, then I can increase the local depth of that bucket. That means one more bucket is created. But in some cases what happens is, there is a collision but already the local depth of that bucket is already same as that of the global depth. Then what should I do? Then I need to increase the global depth. When I increase the global depth, initially the global depth is equals to 2. When I increase it by 1, the global depth becomes 3. That means how many bits I will have to use? I will be when initially it is 2, when I increase it that becomes 3. That means for making a directory structure search, I will be making use of 3 leading bits. When I have 3 leading bits that are considered, initially when I considered 2 leading bits, there were 4 entries, 2 to the power of 2. When I consider 3 leading bits, I will have 2 to the power of 3, that is 8 number of directory entries will be there. That means when the global depth is increased by 1, the directory structure, the number of directory structure entries will become double. So that is the concept here. This is called as the extendable hashing, and of course you can also try with the insertion of other records with the key values 86, 57, 35, 98 and 72 and the appropriate structures which represent the shape of the scheme, or which gives you some idea about how this is dynamically changing is given in this diagram. You can have a look at this and then understand the concepts behind this extendable hashing technique. So the bottom line is, we have a directory structure, we have a hash function, and when a hash function is applied, it will derive a non-negative integer that can be converted to a binary representation, that is called as the hash value. And we have a directory structure depending on the number of bits we are considering in the hash value. If we consider 2 bits, there will be 4 entries. If we consider 3 bits, there will be 8 entries. And then similarly we have global depth and then local depth. Global depth is used to make search in the global directory, and whereas local depth is used to decide upon which block is actually need to be used to store the given record. This is extendable hashing, which is dynamic. And if you carefully observe, like what we have, how we have extended this, expanded this, similarly when the number of records are deleted, then you require less number of space, then the structure can shrink. That means you can deallocate the buckets that have been actually allocated for the hashing. So this is the advantage of this extendable hashing. The second approach is called as linear hashing. In the second scheme called linear hashing, no directory structure is used. Here, instead of one hash function, multiple hash functions are used. That is the difference between the extendable hashing and the linear hashing. In extendable hashing, we use directory structure, and we use only one hashing function, whereas in linear hashing we don't use directory structure, but we will be using multiple hashing functions. When collision occurs with one hash function, the bucket that overflows is split into 2 and the records in the original bucket are distributed among the 2 buckets using the next hash function. If there is a overflow with hash function hi, we will be using hi plus 1 to decide upon the bucket where the data need to be stored. Hence, we have multiple hash functions in linear hashing. Let us have a look at some example that will give us clear idea about how this linear hashing works. We have hash functions h0, h1 and h2 in this example. h0 is k mod 2 and h1 is the next hash function exactly that must result in double as many number of address locations that are available with h0. If I am using h0, the address space contains only 2 buckets, and if I am using h1, that is, it should contain the double the number of locations that were possible with h0. So that's why it should double always. If I am using k mod 2, the next hash function should be k mod 4 and next one should be k mod 8. That is the basic concept. Okay. Now let us assume that the records that need to be inserted are having key values 14, 11, 28, 15, 33, so on and so forth. And what is the result of applying I can use, that is, it is evident that the basic concept of this linear hashing itself says that I will be using multiple hash functions. First I will be using h0, and if there is a collision I may use h1. Okay. So what is applying h0 on 14? 14 mod 2 is 0 and 11 mod 2 is 1, 28 mod 2 is 0. So that's why when I am using the h0, which is k mod 2, that means only 2 buckets are possible, either it will go into 0th bucket or first bucket. Suppose if I am using h1, when it is double the number of buckets, 14 mod 4 is equals to 2. That means now you will have, when I am using 4, it can be 0th bucket or 0 first bucket, 1 bucket, 1 0 bucket or 1 bucket. There are 4 different buckets available. So this is the result of applying k mod 4, and this is the applying k mod 2 on these key values for the records. And further, let us assume that a block, disk block can store only 2 records. Now initially I will be applying only k mod 2, hence I have only 0th record and first record. When I am inserting 14, and there is one more important thing, there is a variable called n, okay, and which will always indicate the bucket that need to be split. That will be split in the whenever n is a variable which points to or which stores the bucket number, which is the bucket that need to be split whenever there is a collision occurring in the system. Okay. Now n is equals to 0, that means this indicates that 0 is the bucket that will be split whenever there is a collision. Okay. Now when I am inserting 14, since I am using only h0, 14 mod 2 is 0, so 14 will get into 0th bucket. 11 mod 2 is equals to 1, hence it will get into this bucket. 28 mod 2 is 0, it will get into this bucket. 15 will get into this bucket. So far it is no collision, no problem. Now when I try to insert 33, when I am using h0, that is, since even now I am using only h0, the hash function h0, which is the first hash function. Okay, when it is time to insert 33, the hash function is h0, that is 33 mod 2 is 1, that need to be actually stored in this one. This will be mapped onto, or this will be hashed onto this bucket, but there is no space available because we know that each bucket can actually contain only 2 records. So what should I do now? There is a collision. Since there is a collision, immediately I need to create a split image of the bucket that is indicated by the variable n. So what is the bucket that is indicated by variable n as of now? It is 0. Hence I will have a split image for the 0th bucket. Okay, there is no problem. And once you have a split image for the 0th bucket, from then onwards, so initially when I am using h0, I will have only 0 and 1. okay, this bucket or this bucket, otherwise I can call it as 0 0 or 0 1. When I am using H1, it could be 0 0, 0 1, 1 1, sorry 1 0 or 1 1. That means I have split images. Now H0, n was initially this one, I have a split image for 0 0 and then I have created a split image. Now actually this is 0 1 2 3 like this, that is integer representation, this is binary representation. Now once the 0th bucket has a split image, now I need to distribute the records that are available in 0th bucket among this split bucket, this split bucket and this bucket. When I do that, 14 will get into this, 28 will remain here. That means when I am deciding upon which bucket to be used for the split image, then I must use H1. That means when I am using a hash function H0, when it is mapping onto 0, since it is already split, I need to apply hash function H1 and 28 will remain here, and that is the redistribution of the records. And once splitting is done, the automatically n is incremented by 1. Now n becomes 1. That means what? The n indicates whenever further collision occurs, the bucket that need to be split is the first bucket, that is 0 1 bucket or the second bucket in the array. Okay. Now when I am inserting 33, there was a split and I could still 33 is still there with first only. Though there is a collision with this bucket, the splitting has occurred with bucket 0. That is the important point to be noted here. So I have a overflow bucket for this, that is a limited amount of overflow is still possible, and I have a overflow bucket and I have added 33 here. When I am inserting 46, 46 will be mapped on to, when I apply H0, it will be mapped on to 0, but 0 is less than n. It indicates that this is already split and then split image is available for that, hence I need to apply the H1. When I apply H1 on 46, that is 46 mod 4, it will give me 2. So 46 will get into the second bucket, and this way we consider. Now whenever there is a collision, what is the bucket that will be split? The bucket that will be split is this bucket, so it will have a split image and this overflow bucket is gone, and the records that are available in this original bucket and the overflow bucket are redistributed among this original bucket and the split image of that bucket using the hash function H1, and this is called as redistribution. And this way now the overflow bucket is gone and it keeps on increasing, that is we can expand or shrink as and when it is required. But we split the buckets in a specific order, and independent of the collision, the bucket where the collision occurring, the bucket that we are going to split is the one which is indicated by the variable n. That should be kept in mind. That is very important point. Hence the bottom line is we have multiple hash functions in linear hashing, and when there is a collision we will apply we will split the bucket, okay, which is indicated by the variable n, and the split image is created, and we will, by applying the next hash function, we will redistribute the records in that split bucket among the original bucket and the split image. And we always perform splitting in a particular sequence independent of the bucket where the collision occurs. Okay. Once all the buckets have been split or all the buckets have split images, automatically what happens? Again n becomes 0. Since all the buckets have been split and every bucket is already having a split image, then we don't have to use H0 at all. Now we can straight away start using H1. If there is a collision, again we will be using H2 and the n will be increased, and that will point to the next bucket to be split. So this is the concept behind linear hashing, and carefully examine and understand the example given in this slide, and you try how this is working with the other records with 15, 33, 46, 8, 21 and 4, and this is the final shape of the linear hashing scheme that gives you complete understanding about this linear hashing technique. So in this session we discussed what is hashing technique. Hashing technique is there for fast retrieval of the records from the database. We can hash files. we can apply this hashing technique on data files. Such files are called as hashed files. We have internal hashing, which are used for files on the RAM. We have external hashing, which is used for files on the disk, hard disk. And we have seen static external hashing, where we will be using a hash function and the number of buckets or address space is fixed. As and when collision occurs, and we will be resorting in chaining, and more number of collisions will result in more amount of chaining, which will basically defeat the purpose of the hashing. Hence, to solve that, we have dynamic hashing, where the address space can be expanded, or it can shrink depending on the requirement. That is why the performance wise it is far better than static hashing. In dynamic hashing, we have extendable hashing and then linear hashing, which are dynamic. In extendable hashing, I will be using a directory structure and a small amount of chaining, and in linear hashing I will be using multiple hash functions. Still small amount of chaining is still possible here in linear hashing also, but the amount of chaining that is used is very minimal. That is why the performance will never degrade when we use this dynamic hashing techniques. Okay, let us stop here. In the next class we will have a complete discussion about the other retrieval mechanism which facilitates fast retrieval of records from the database, which is known as indexing. Both hashing as well as indexing are meant to serve the same purpose, that is fast retrieval of the records from the files. Thank you very much.